So what we were discussing that firstly, how the half sandwich complexes of thiophene is being formed. So as I mentioned at the very start that since 4 electrons are coming from your 2 pi bonds and 2 electrons are coming from your sulfur, so in total it gives you a 6 pi electron system. That's where it is being called as isoelectronic with C5H5 negative. And when we are treating it with chromium carbonyl group and we are giving a thermal energy, as I mentioned, it is not that easy to remove your carbonyl center if it is very tightly bound with your metal center, and add a thermal energy or a photo energy. That means in presence of light source, when you are employing 6 electrons, you need to remove the 6 electrons from your original substrate. So 3 carbonyls will give you 6 electrons. That's where 3 are going out and other 3 are left out, which is making a proper complex with chromium. 6 are coming from here, 6 are here, and other 6 are here. So it gives you a total 18 valence electron system. If there is any doubt, please let me know.
Actually, I have a doubt in slide number 76, ma'am.
Okay. Yes. Yeah.
Can you kindly calculate the valence electron for that, ma'am? Binuclear complex.
Yeah. So here, if you'll see, if I'm talking about an eta 3 system, just a second. So nickel is known to make a very stable complex of 16 valence electrons. Generally, you might have seen that if I'll talk in a layman language, when we talk about an octahedral system, nickel generally comes in a square planar system. You might have heard it, right? So in a square planar geometry, it would resemble to have a 16 valence electron. So that's why to have a 16 valence electron, to maintain that, 3 electrons are coming from above, 3 are coming from down, and nickel itself gives you a 10. That's where it is making a 16 valence electron in both the sides. And that is why the reason is to have a nickel dimer or this particular bridging complex with an eta 3 coordination of C8H8. So only 3 centers are participating. When 3 centers are participating, that means it is only involving 3 electrons from both the rings, 3 from above, 3 from down. And nickel, since its atomic number is 28, that would give you 10 electrons. If you calculate 10 plus 3 plus 3, that's a 16 valence electron.
Okay, ma'am. And the next one is in the previous slide. You said that the triple bond.
Yeah. So,
Yes, ma'am. And that binuclear chromium,
yeah.
that alone, ma'am.
Yeah. So actually, as I mentioned, this is not a thumb rule that in all the bridging systems, we are expecting to have a metal-metal bond or the C8H8 has to be in eta 3 or eta 5. So with different system, different metal system, as you saw, the reactivity is different. Their bonding properties are also different. So in case of if you are having a chromium or a tungsten, in those cases, they bound to make an 18 valence electron. They generally prefer to have an 18 valence electron stable system. So that is why it is said that generally if triple bond is existing between two metal centers, it would tend to make an 18 valence electron. How it is making 18 valence electron? Because from the terminal groups, it is participating with 4 electrons, 4 centers, and other C8H, which is in bridging form, it is taking 5 from that bridged one, which is not in the case of nickel, because in the nickel one, that's why I have not merged all the 3 examples in one. Chromium and tungsten, they are forming one type of bridging complex, whereas C8H8 with the nickel system, they are forming, because here the 2 rings are in bridging one. The above example is different. There is only one system, is one C8H8 is in bridging one, and there is terminal also. Here there is no terminal group. Only the 2 bridging ligands are there. Second point is chromium, tungsten, and iron. They tend to form an 18 valence electron mostly in most of the cases. Now, I won't be saying like in all the cases, but mostly it would prefer to form an 18 valence electrons. Whereas titanium, if you'll see, it would form an 16 valence electron. Similarly, nickel also prefers to have a 16 valence electrons, and there is no metal-metal bond. It is not something that we have predict on our own. It's something when they have got the crystal structure, those people, like say for example, Kruger has invented this. they have got the crystal structure, they have seen the properties that there is no metal-metal bond existing between the two nickel centers. And how it is stable? Because only three centers from both the rings are coming into picture. They are coordinating with momentum. I understood your question that it would be difficult if you are having a bridging system, and that's not a thumb rule that in all the bridging systems it is going to make only eta 3 and eta 5. If at all it is only the bridging C8H8, there is a high possibility of having an eta 3 or eta 5 bridging the centers, the hapticity. But if you're having a mixture of both terminal as well as the bridging one, there is a possibility that you need to calculate the total valence electrons, and then you will be able to say, okay, how many centers they can coordinate with. Either it would be eta 4, either it would be eta 5, because in the above one, this is also bridging, right? So here it is participating as an eta 5 for both the metal centers, because it has to stabilize its valence electron. Whereas in other case, in nickel, the only demand is for the 3 electrons. That's why the eta 3 is working.
Yes, ma'am, I understood, ma'am.
Okay. So is this clear, what we have seen in the half sandwich case of thiophene? Then we can move ahead.
Yes, ma'am.
Okay, great. Now taking in another example for N heterocycle is your, now we are talking about N heterocycle, which I already mentioned, which is a pyrrole anion. So pyrrole anion meaning C4H4N minus. Actually, pyrrole is your C4H4NH, and when you are deprotonating it, it forms as N minus, and this is also a 6 electrons, because 4 electrons coming from the pi electrons and a minus charge lone pair. And this is isoelectronic again with your CP ligand, which is C5H5 minus. So how it forms? If you take 2 moles of pyrrole system and you're treating it with Mn2CO whole 10. This is a dimeric complex of manganese, and it would end up making Mn and complex with pyrrole and 3 CO ligands. If you will calculate here as well, it is going to give you 6 electrons. So this is the 2 molecules that we are going to come in that picture. 6 electrons are going to come from your pyrrole. Manganese is your 7 electrons, and 6 are coming from your 3 carbonyls with the release of a hydrogen gas, because 1 proton and another H, because 2 molecules we are taking, so they will form a hydrogen gas with 4 CO, and this complex is known as a cyclopentadienyl metal complex, which has been given by Austin in 1962. Moving ahead with the preparation of your this system. So we are talking about the preparation of N heterocycle. So we are taking an example of C5H5 iron CO whole 2 iodine, and when we are treating it with, or we can have a minus charge directly here, and K positive, this would form C5H5 is nothing but your CP ring. The 2 carbonyls, this would Ki would go out, K positive and iodine negative, CO, and then we are having a bonding with our nitro N heterocycle. Now, if at 40 degrees, we are giving a temperature of 40 degrees, what would happen? Or if we are giving lambda 500 nanometer, meaning we are giving a source of light as well. If we are giving heating, it would release the 2CO outside. If we are treating it with light, at this particular lambda is high, energy is less. So it would regain the 2COs and ultimately it would form iron, FeCp, and the whole molecule will come and bind. Because here it is only binding with two pairs, the two electrons of the nitrogen. So if you calculate, this is going to give you 5 electrons. So here if you will calculate, if you are only considering, since we are calculating only the binding centers, so it is 5 electrons. These are going to give you 2 electrons. This is 2 electrons. And here it is binding with, okay, this has to be remade. So this is actually making a sigma bond with your nitrogen center initially because this was having a negative charge. So this is 1 electron, this is 2 electron, 5 and 5 coming from the ligands is 10 electrons, and iron is giving you 8 electrons. It is making an 18 valence electron. Ultimately, when we are giving a thermal temperature, it is releasing the 4 electrons from here, and this hapticity is going from eta 1 to eta 5. When it is going from eta 5, now eta 5 are here as well, both 10 and iron center as 8. Again, it is making an 18 valence electron with a loss of 2 carbonyl centers. If there is any doubt, please let me know at this point itself so I can help you in understanding.
Yes, ma'am. In the last slide.
Yeah. Okay, I'll try to explain it again. So firstly, if you will carefully see over here, there are different ways you need to see at which way your ligand is coordinating with your metal center. So if you have a coordination like this way, because at no point of time at the formation you are giving any thermal energy or any light source to remove your CO. So ultimately it is only going to remove the iodine and introducing another N minus. It's just a nucleophilic substitution. I minus is going and N minus is coming. Is that clear at this point?
Yes, ma'am.
Okay. So once this is done, and then you can calculate your number of electrons. It is 5, it is 8, it is 2, 2, and 1. So it is giving you 8 in valence electron. Now I'm saying I'm providing an heating of 40 degrees. And whenever we are giving a thermal energy or a light source, it would release your CO. If there is any possibility of the hapticity being changing, as we were mentioning in case of C7H7 also, here it is having a hapticity of 1. But we know that it can go to eta 1, eta 3, and maximum eta 5, meaning it can involve 4 more electrons, which are the pi electrons. So these two molecules, in presence of the heating, that can go out. So 2 molecules of CO will go out, and ultimately it would form a group which is involving all the 5 centers, including the nitrogen. So now the hapticity has changed from eta 1 to eta 5. Therefore, if you will calculate the total electrons now, 5 are coming from Cp, 5 are coming from pyrrole, and 8 are coming from iron. Again, it is making an 18 valence electron, which is a stable system. Now at this point, have you understood at this point?
Yes, ma'am. I can understand here, but in the previous example where manganese is used as the central metal,
Yeah.
there the valence electron, when we add up, it's coming to be 19 electron, ma'am.
Some
6 plus
complexes,
7.
yeah, some complexes in manganese case, we have also seen that some complexes with the half sandwich or with the sandwich, there are every time there would be some exception with the, I wouldn't say exception, it's like some systems they stabilize in different valence electron configuration as well. So here I do agree that it is making an 19 valence electron system. So this is possible in case of manganese, but this is not possible in case of iron. We have also seen in some triple decker complexes where we are having a 30 valence electron where 2 metal centers are there, 20 valence electrons. For that reason, you need to, if you have watched the earlier sessions, then you might be seeing some many examples with manganese or with nickel, where they are increasing the total valence electron. So as I mentioned, some systems they form a 16 valence electron. Some will stabilize in 17 as well. We have seen a vanadium complex which is stabilizing 17 valence electron as well. So it depends upon the property of a metal center. Generally, it is 18 valence electron or a 16 valence electron, but it is not true for all the cases.
Okay, ma'am.
Yeah. Okay.
Yes, ma'am.
So this step is clear. And at this point of time, if we have this particular system, now earlier we gave a thermal energy, and if I again give this particular complex energy, some light or some wavelength. When we are talking about a wavelength, that means we are providing an energy source, because h nu is when you're talking about light is having both the component of lambda as well as nu. So when this is a scenario, at that point, it can regain your CO. If you're adding two more COs, it would go back to its original substrate. So this is also possible. So you have to be very careful when you're treating the CO ligands in presence of thermal energy as well as in light source, right?
Yes, ma'am.
Okay. So moving ahead to our next system. So the last topic of our today's session, which is the introduction of the coupling reactions. So this is, I think, the final topic of our this course, but that would be taken in proper description for all the pending next 5 sessions. I think it is going to be on to the coupling reactions, which is a very, very important part of the organic, inorganic, whatever the chemistry you want to say. So we are starting with the CC coupling reactions. So today will only take an introduction because it's already 7:32, and we will be having some minutes for solving the questions. So I will just introduce what are the different types of coupling reactions that we are going to talk about. One is Heck coupling. Don't get overwhelmed with the names. We will be able to remember the names if we know what kind of catalyst and what kind of substrates it is going to use. Still coupling. Sonogashira, you might be aware of this, and dehydrocyanation. These are the major coupling reactions that we are going to talk about it. So what are the features for these reactions generally? Uh, Here, these are essentially in organic synthesis, as I already mentioned. And generally, palladium is the one which is mostly used catalyst in these reactions, because it has the feature of tolerating many functional groups. Meaning, if you have a lot of functional groups in your substrates, so it won't give you another product out of it, or your functional groups are not going to be affected. It's like protecting your functional groups if you are using this kind of catalyst. Palladium compared to other metal systems, the 45D, if I would say, it is having low toxicity, but not the whole toxicity has been removed. That's where many new research is going on with 3D metal systems, which are known to have less toxicity and they are cheaper compared to the palladium. But palladium is known to have its own inherent properties, which can give you the product in at a very faster rate. And it's economical if we compare with the even more expensive metals like platinum, iridium, rhodium, etc. So these are the features of the coupling reactions. So general reaction we will take up. So earlier, if we talk about the stoichiometric ratio, how the reaction in why a catalyst is needed in these reactions in a stoichiometric fashion, how you can expect the reaction is going to take place. So you have an Rx. R could be any alkyl, alkene, anything like that. It's a positive and this is negative halide. And you're treating with any metal source which is zero. What it would form, it would earlier form a Grignard reagent as RMgX, where your now X is participating as a minus charge. So the valency, the charge has been changed from the positive to negative. Now, when you're treating it with any electrophile group, so it would bind with your, since it is R negative, electrophile would be positive. It would attack onto your electrophile and it would form REL product with YMGX. Y could be another source of X halogen. So like MgCl2 or MgBr2. But in presence of the catalyst, if we are going through a catalytic fashion, So catalytic fashion, actually what a catalyst does. So if your reactant is here and your product is here, you generally, this is your energy barrier and it has to cross this well to come to this level. So this much energy it has to cross, this much energy it needs. But if you have a catalyst, it might go just like this way, depending upon the property. So this much energy it is required to cross in presence of your catalyst system. So in catalytic fashion, you have, say for example, substrate as Rx. Now you're taking a palladium. Now this palladium would make palladium 2. It would undergo an oxidative addition. You might have heard about this as well. Oxidative addition would make your metal center to go from 0 to +2 state, as it is going to take both R and X into the picture. Now, in this case, you're treating it with nucleophile and another metal. What would happen? The metal and this X will go out, and nucleophile will go and bind with your palladium center, because your metal is in that particular state that it can attain the nucleophile. Ultimately, it would undergo a reductive elimination. These are different processes. Here it is 2. Now again, when our nucleophile will go out, palladium will go from +2 to 0 state. So this means that we started with palladium 0, we end up having a palladium 0, meaning your metal system or the catalyst has not gone used in the catalytic cycle. That means it can be reused for your system for the multiple cycle. That is where the catalytic reactions are now being taken into very, very serious way, because when you're not consuming any reaction but it is happening at a very faster rate, requires very less energy. Because in earlier case, when you're doing a stoichiometric reaction, it did form your product, but it would make another species and it is no longer mg0 and it cannot participate with your left out amount of the substrate. Here in this particular scenario, I used one molecule of Rx, I got my product, this product. Now my palladium 0 is again there. If another molecule Rx is there, it would again react with palladium 0 and it would continue to make my product in a more easy and sustainable formation. So this was the difference between the stoichiometric reaction as well as catalytic reactions and how the coupling works. So this we will be taking in our next sessions. From next week 8 sessions, we will be talking about the coupling reactions. So is there any doubt or confusion for that? Otherwise, we can move to the problem session.
No doubt, ma'am.
So, since A7 week sheet, I believe that you guys have read the questions already. So we are going to take those examples directly, and we will see whether you are able to answer the questions, because none of the questions, it's not that difficult that you will not answer it, because everything we have taken and even described in a proper manner. So try this question where you have a titanium complex. You need to understand the ligands that you are taking and what kind of reagents it is having. So here we have a C5H5, and here if you see it is C7H7, and it's a titanium system. Now the first step is having a lithiation, because you are giving a butyllithium in presence of a base. So what do you expect? What is going to happen?
So lithiation takes place at C7H7
Yeah,
ring.
that is the scenario when we are not giving any base, right? In absence of base, it is bound to have a lithiation at C7H7. You are actually correct. But when you are having a very strong base, so what do you expect? Like protonation is going to happen from only at C7H7, or it is going to take the proton from C5H5 also and then lithiating it?
And as it's a strong base, it will take place both at CP and C7H7 ring.
Right. So once this lithiation has happened, both at CP here as well as, or I can write here as well as this side lithium. Once lithium is there and you know that it is giving you an R2P Cl, Cl is negative, 2 lithium chloride would go out. What you will end up having at both the positions. So which option is correct? Now, in place of lithium, add your Pr2, because in place of that, your Pr2 is going to come, because that is the electrophile which is going to replace your lithium. Hello.
Yes, ma'am.
So, why are you able to answer this question? Which of the answers would be correct? So, you are right in saying that lithiation would happen at CP group as well as in the second C5, C7H7 as well. So, you can consider that lithium is here and lithium is here. Now, in the next step, you are having an R2PCl, where Cl is having negative charge and lithium is having a positive charge. Lithium Cl will go out, lithium chloride will precipitate out. What would be the step for left out? Only R2P, which
Yes.
is with the positive charge.
That PR2, lithium will be replaced by PR2, ma'am.
Yeah, so the
So
option
option B.
is correct, right? So in this regard, this way only you will be asked questions in your exams also. Now the next question, the most appropriate reagent for the given transformation. This is very straightforward. If you will see your substrate, there is a metal center. The other one, there is an rhodium carbonyl group, which we already discussed that here three centers were involved since it was having a left out four coordinations which are coordinating with the rhodium. So what would be the possible system? Firstly, you need to see where you are having a carbonyl. Ultimately, if you just, even if you don't know the equation, you just see the option that has been given. Only the second option is having a carbonyl group. Other ones either having a cyclooctadiene, another one is having an oxide, and last option is having a phosphine. But in your case, the bonding is with the carbonyl. So option B is right in straight away answer, isn't it?
Yes, ma'am.
And if you know the proper logic about it, we have already discussed that it's a dimeric structure. And whenever you have a hapticity which has not been fully used, like C7H7, seven centers are there, only three are being coordinated, four are still left, and you are treating it with some dimeric structure which is having a possibility to coordinate with your C7H7, it would always form this kind of structure and having a metal-metal bond. So yeah, this was the substrate because they were the given the options. Metal is same, but only one option is having a the carbonyl group. Other options were not possible in this scenario. Now, in this particular question, in the scheme given below, the carbonyl substitution is felicitated by. So you just see the reaction and try to answer firstly how it is going from. Firstly, we have eta 7. Now in eta 7, then it went to eta 3, and then when we give a light source, again it has a eta 7. So what it actually happening? First option is stronger binding ability of p bound ligand, because the question it is saying that given below, the carbon substitution is felicitated by what? Haptotropic shift of the cyclopenta heptatrienal ligand, increased steric crowding in the product, change in oxidation state at the metal center. So what do you think what has happened?
Haptotropic shift of the cycloheptatrienal ligand.
Yeah, you're right. Because if even if we don't see the options, we clearly see that okay, it is going from eta 3 to eta 7 to eta 3 and then coming back to eta 7. Also, if you'll see other options, they are wrong. There is no stronger binding ability of p bound. If you compare the phosphorus binding and carbonyl binding, carbonyls are pi acceptor ligands and they are very very strong bound with your molybdenum. So until unless you give a very strong source like be it thermal energy or light source, it will not cleave out. So the option is anyway wrong. The third option, increased steric crowding, is helping. That is also not true because this is not that much stirring which would help to carbonyl to go out because it is forming an 18 valence electron at this place also. And change in the oxidation state. If you clearly see over here, the oxidation state is not changing at all because both carbonyl group as well as the phosphorus group, they are neutral ligands. None of the places the oxidation state of your metal center is changing. So it is only the one option. Besides, even if it is true that looking at the substrate or the reaction scheme, you know the answer, it is always advisable that you understand the other options as well, whether there is any possibility that other options could be true or not, because sometimes there are multiple choice questions and answers are being asked. So you have to be very careful with the options as well. So moving ahead with the fourth question, choose the correct statements. As I was mentioning, choose the correct statement or statements for cyclooctatetraene ligand. So first is in its caught in its planar shape, it donates 8 electrons. B option, it can act as a terminal ligand. C option, it is aromatic in its tub shape. And D is cannot act as a bridging ligand. So I would ask in this manner. When it is
Regarding the first statement, when it's planar, it donates 10 electrons.
right, it gives 10 electrons because it becomes C8H8 2 minus. Right.
Yes, ma'am. And regarding the second option, it can act as a terminal ligand. It is correct.
Yeah.
It is aromatic, but
Is it aromatic?
and yes, ma'am.
No, it's only aromatic in its planar shape. In tub shape, it can't be aromatic. Tub or puckered shape, which we saw, right? This
Yes, ma'am.
cyclobutadiene shape. So in this particular shape, when it is not a planar thing, only the planar moieties can be aromatic in nature because they will form the Huckel's rule. Otherwise, this will not form in Huckel's rule. So in tub shape, it is not aromatic actually. So this is wrong. The first is wrong. Third option is wrong. It is only aromatic when it is planar, and it cannot act as a bridging ligand. That is also wrong because it can act as both terminal as well as bridging ligand. So only the option B is correct. Is that clear?
Yes, ma'am.
Okay. Then try the question number 5th.
Yes, ma'am.
So the complex we have with zirconium, where one C8H8 is eta 8, another is eta 4. So you need to find out whether it's an 18 coordination compound. So zirconium comes in which category? It belongs to titanium group.
It's
And
16 electron compound,
right,
ma'am.
it's 18, it's 8, it's 4, and this is also 4. So it becomes a 16 valence electron. So option A is incorrect. Does it form an adduct with THF, NH3, NCr? Yes, it does. It does form the adduct formation. That means it is having that kind of, it gets stabilized whenever lone pair containing group, it is going to attack onto this one, because the adduct meaning it is not forming a very, very stable. At any point of time, the molecule can go out. And THF, if you will see, it is having a lone pair. Sorry for this. 1 second. So it enhances the electron density onto this one. So if you have tetrahydrofuran, sorry, this is, if you're making like this way, so it can give you your zirconium 2 more electrons. So it does form an, because it's a deficient system. So it forms an adduct with the system which is going to give you the lone pairs. So this is correct. It's just like the titanium. Titanium also tends to form sometimes adduct because it is highly deficient. The third option, that both cyclooctatetraene moieties bind the metal center in the same fashion, which is not correct because one binds as eta 8, other binds as eta 4. And D is, it's a high valent compound. No, it's not a high valent compound over here. So this is also not correct. So I hope
If it is when the total valence electron comes as 18, then it becomes high valent compound. Is it right, ma'am?
uh yeah, you can say that way. High valency is also coming when the charge is there, because generally titanium and zirconium, this they would prefer to have a plus for oxidation state, right? So that time we can say that okay, it's a high valent system. So yeah, in this particular case, when it is not achieving that particular oxidation state, that time we can't say that it's a high valence system. So here, if you will, even if you consider that eta 8 and eta 4, if it is, say for example, generally we saw that C8H8 can act as a neutral ligand as well, right? So here eta 8, when it is binding as an eta 8, that means it is giving a 2 minus charge. It is having 2 minus charge because it's a planar. Whereas eta 4 C8H8, it's a neutral, which is 0. So which is giving your zirconium as 2 positive, right? So generally, titanium, zirconium can attain a maximum oxidation state of +4. So high valent means when it goes oxidation state which is higher than the normal oxidation state. So titanium, zirconium, they have a tendency to go for +4. Say for example, palladium. Palladium can also achieve from 0 to 2 and +4. So that's the high valent compound. Here it is not, because it is only having a +2 state. If at all both the C8H8 would be in eta 8 state, then we can say that it's a high valent system. Right?
Actually, in this example, if the zirconium gets +2 oxidation state,
Yeah.
then from 16 valence electron, it will still more reduce to 14 valence electron only, no ma'am. Then
No,
how can it be a high valent compound?
no. Actually, if you are calculating the oxidation state, then you have to consider the charges of your ligands as well. I think this is the right question that we can introduce. So what we are considering, it's a C8H8 eta 8 and eta 4 C8H8 and zirconium, right? So when I'm saying that if we are going by oxidation state method, then we need to see the charges of everything. So in eta 8 C8, what is the charge on the ligand? Is it neutral or it's 2 minus? Your eta 8, when we have an eta 8 system, C8H8, it becomes
2 minus
neutral.
1.
So it is 2 minus, right? So now if you'll calculate, it is 8 plus 2. No?
Okay, ma'am.
Right? So what you were expecting, that in earlier cases, when you are seeing, you are not including the charges either of the metal or of your ligand system. When you are including the charges, then you have to include the charges of your ligand as well as the metal. Then when you consider the zirconium as a +2 or +4, depending on that, the electrons would be changing. Understood? So you go by either of the methods. It is better to always go by a neutral method where you're only considering the hapticity, the number of electrons. It is coming from the centers, not including their own charges. Because when I'm talking with zirconium, I'm taking its full number of electrons, like 4. I'm not talking about zirconium in +2, zirconium in +4. If it is zirconium +4, that means 0 will come into picture. If it is +2, only 2 electrons are going to come into picture. Like in this particular case, if I have taken the charges, it would give you 4, and here it would consider as 0. So it would consider as 2. So now if we'll calculate, it is 8 plus 2, 10 and 16, right? If I'm saying at all, it is +4. So from where the +4 is coming into picture, there has to be increased. Understood? Earlier, when we were not taking any charge into system, that time it is only having 8 and 4 and 4. When you're including the charges, then you need to know the metal oxidation state as well. So based on that, then you will calculate the valence electrons. Is that clear?
Yes, ma'am.
Say for example, you can take an example of, say for example, Cp and CO whole 5, CO whole 3. So generally we say iron is 26 electron atomic number, 8 electrons coming from iron. Cp will give you 5, which is already 13. And sorry, here it would be. So if you are
Here it's coming as 19 valence electron, ma'am.
if it is 13, and then you have 4 coming from carbonyl, that is 17, and then you have one more chlorine. If I'm taking, this is 1, right? So this becomes 18 valence electron when I'm taking in a neutral fashion.
Yes, ma'am.
Now consider Cp gives you 1 minus charge, Cl gives you 1 minus charge, right? So that means your iron is in +2 oxidation state. Now calculate with respect to the iron method. Now iron in +2 oxidation state, how many electrons it would give? That would be D6 configuration. Only 6 electrons will come.
Ma'am, your voice is not audible, ma'am.
Hello. Can you hear me now? Hello.
Yes, ma'am. You're audible now, ma'am.
Yeah. So what I'm saying is, earlier we saw, in this particular scenario, we saw like we are not considering the charges and we only took the valence electrons at 8, 5, 4, 1, right? Now consider the ions. When